Okay. So good morning again, and sorry for these problems. I hope that we'll not face them again. As Senna suggested or introduced very nicely before, I will talk about fatigue of composites today. Actually, fatigue is a huge area in science, in our life, everywhere. Actually, today, what we can do in 45 minutes, we can only give an introduction to fatigue, starting from the early times and come briefly to where we are today with fatigue of composites. So we'll just introduce myself first. My name is Anastasios Vassilopoulos. I'm a professor at the École Polytechnique Fédérale de Lausanne, is the technical university, one of the two federal universities of Switzerland. And I'm working with the composite construction laboratory in the civil engineering department. Actually, it's a laboratory working with all FRP structures, composite structures in any kind of application. So I'll pass to the next slide, which is actually an introduction of what happens in reality. Whatever has a physical activity, either human or animal or material, actually is getting fatigued, is getting tired. And this is the gradual sequence that we follow from our birth to our death. And exactly the same happens to materials. They come in life, we make structures, and finally, after a certain time, more or less the same for same materials or same structures, we have the failure, which for materials we call it failure, for human beings we call it death. So this is inevitable. What is obvious in reality is that fatigue is known since old times. I suppose you recognize this person there. I already gave a hint. And can you tell me who is this guy? Or what he did? Any reaction?
No.
Okay, this guy is Philippidis. The name is there. And this is the one that ran the first marathon in 2,500 years before today. And actually, what he did, you probably know about this Battle of Marathon. It was the Greeks, ancient Greeks, against the Persian army. And Philippidis, this guy here, was the postman of, if you like, of the battle, and he had to go from Marathon to Athens, so run this distance here, which is exactly 42 kilometers, to ask for help. But the Athenians of that time, they told him that they were very busy, they couldn't help him. So what he did, he ran from Athens to Sparta to ask for help. And the Spartans told him that they couldn't do anything because they were busy. And then he went back to Athens to say that the Spartans didn't. And then he went back to Marathon. But when he went back to Marathon, the battle was over and the Greeks won. So he had to go back to Athens and announce the good news to the king. He says, the Greece has defeated the Persians and I totally crushed my daily step goal. And then he died. So he was a very good runner. Why did he die? Can anyone tell me?
Fatigue.
Huh? Yes, fatigue. But what I mean, why he could run so many kilometers and die after all this? And in reality, what we do in our life, we run more kilometers than him, but we don't die because of this fatigue. So what is the difference between these two elements?
He was running continuously.
Can you speak loud?
Because he was running continuously, it's not making a break or something like this.
Exactly, he was running continuously, so he was not getting any rest. Huh? Have the same. Have you ever seen this movie? You recognize this guy here. This is a bit recent, more recent than Philippines. This is Forrest Gump. Probably you didn't see the movie. If you didn't see it, it's
We saw.
so for him, what was happening, he had some problems, and then he had to run. So and he ran all these kilometers. You see here he ran America 4 times up and down. So he ran more than 5,000 kilometers, more than what Philippines did, but he didn't die. And the difference, exactly as you said, is what he said during the movie. He said, when I got tired, I slept. When I got hungry, I ate. When I had to go, I went. So this is the difference.
Asush, the sound is not so good now.
My sound or the...
Yours. Probably was because of the video, probably. I don't know why.
Now it's better?
Can you go to the next slide? Because probably Zoom tried to adapt to the...
Now it's better?
Now it seems better.
If it is not better, I can stop and start again. But
No, now it's better. Now it's better.
Okay. So now we come to the material behavior, and as we said before, materials behave like humans, so they get fatigued. And the investigations that we are doing is exactly to understand, so we torture actually the materials, and we try to understand their fatigue behavior, how they behave under fatigue loading. And in exactly the same investigations as we did before, we have now the proof that if we load the material in a continuous way, the material will fail after a number of cycles. If we load the material at the same stress level, but we interrupt the stress or the loading at specific times, then the material can support much more cycles. So this means that the material itself has a mechanism of relaxation. So the material, when we unload it, and this is specifically for composite materials, but we've seen it also in other types of materials, when we unload the material, it has a kind of mechanism to relax and regain, if you like, a potential for additional lifetime. So what is fatigue? This is, we introduced it somehow, but what is fatigue? Can someone, I know someone that has this problem for a long time. What exactly is fatigue?
It's accumulated damage under cyclic loading.
Accumulated damage. Anyone else? Actually, today, although we investigate fatigue for 200 years, we don't really know what is fatigue. We still try to understand. We still try to realize why fatigue is important, but still we do not know. And fatigue has been, as I said, we investigate fatigue for a long time, but it has been introduced in the dictionaries, or it started from the ASTM, the American Society of Testing and Materials Dictionary. And we have a definition only in the 1946 or something like that, where they define the phenomenon under which properties of a material are deteriorated or degraded due to cyclic loading. Exactly as you said before, we have accumulation of damage, not necessarily structural damage, but it might be also viscoelastic damage to the material. And this reduces the material properties during time. So you see, I introduced now 2 different terms. We have load and we have time. So fatigue actually is a combination of structural damage and viscoelastic damage, viscoelastic phenomena that both work together. So as we say, synergistically to create or damage in the material to damage the material itself and lead the material to failure. So we said failure, and if we see, I just said before that we investigate fatigue for almost 200 years now, and still we don't know a lot. And this means that even today, fatigue failures continue to occur. We have a lot of examples of failures today that can be attributed to fatigue. And actually, there are a lot of investigations showing that 80 to 95% of structural failures are due to fatigue or fatigue-related phenomena. What is a fatigue-related phenomenon? Can you understand this meaning?
I couldn't hear the question, Professor.
I just read here the last bullet saying that it is well documented that 80 to 95% of structural failures are due to fatigue or fatigue-related phenomena. We defined more or less fatigue before, and I'm asking you to define the term fatigue-related phenomena.
Crack propagation.
Hmm?
It's probably crack propagation.
Yes,
Crack propagation is fatigue. Eh?
yes, initiated and regulated, but there's no fatigue.
Hmm? I mean, the response is written just in the following sentence, where we say that most of them are unexpected failures. So fatigue-related phenomenon is a failure which is not directly fatigue, but is due to fatigue. So I'm coming back to a very simple case. Probably all of you did this. You have a paper clip and you play with that. So what we do when we play with a paper clip, we fatigue this structural material. Is it correct? I have a paper clip. I can find one here. And I start. Come on. I'm sure you've done it again. All of you did it when you were at school and you were bored, like now, probably someone of you are doing now. I have the paper clip here, and I'm playing with that. I'm bored. So if I do it a lot of times, probably I will break it. But I stop doing this, and then I just pull it or bend it. I will break it, and the breaking force that I will apply, or the bending moment that I should apply there, it's much less than the bending moment that I should apply to the same paper clip if I don't first. So if you remember, probably you've seen it in some of your courses, the problem of fatigue in axles. You have a metallic steel axle of a train, for example, and we rotate it and we bend it. So we create fatigue loads. If we see the failure surface, when it fails, the structure around it has cycles of damage, which are fatigue damage, and then the middle of the circle is roughly is rough, because at the end it fails at a bending moment that cannot support anymore, because the structure has a cross section which is less than what it was before the fatigue. And this is what we call a fatigue-related phenomenon. We'll see also later on some of this, but only to clarify the terms. So we said 200 years, and if you see, we have the early fatigue failures already observed almost 200 years ago. One of the first ones was this derailing of a locomotive axle. It was a train that was coming back from Versailles to Paris after having some celebrations for the birthday of Louis Philippe. Actually, Louis Philippe was the last king of France. I don't know if it is related to this accident, but this accident has been attributed actually to fatigue failure, because of the one of the axles has been failed due to fatigue. Keep this date, 1842. So exactly this is what I described before. The axle around has been fatigued. And then when the cross-sectional area was not enough to transfer the loads that was supposed to transfer, it was failing in an abrupt way, very sudden way. And that's why we see here this roughness in the surface. So we've seen also similar failures during the World War II with the Liberty ships. A lot of them were very rapidly produced by the United States to supply food and materials, but they had a problem because they were all welded, and there were cracks that started from the corners of rectangular hatches that they had, and these cracks during the floating in very cold waters were propagating in fatigue crack failures, and led a lot of these ships to the bottom of the sea instead of the Allies. We also have this very famous fatigue failure, which is probably the first passenger jet in 1954 from the Havilland Comet. And there, the problem was exactly the design of the windows. The windows were rectangular, and in the corner there of the window there was a crack that was propagating during the airplane acts as a pressure vessel. So it pressurized and depressurized. So we have stresses at the cell of the airplane. And because of this, actually, because of this failure and the post-mortem investigations, now they design the windows like, the new window frame of this airplane was circular, and now we have these windows that you've seen in airplanes. So what is the message here is that if you see an airplane with rectangular windows, take the next one. Huh? So this is what they found once in the bottom of the sea from this airplane. And this is now in the Science Museum in UK. And they actually found cracks running from the corners of these windows to the fuselage, to the rest of the structure. And another quite funny, if you exclude one person that lost her life, one steward, is this damage, this fatigue damage. It was actually an airplane in 40 years ago, actually 30 years ago, that was flying in Hawaii Island from Honolulu to Hilo Island, that is written there. And actually, oops, the other way around. What happened? The airplane opened like that during flight. And why did it open like that? The investigation showed afterwards, and I have it written here, that the plane was designed for 20 years lifetime, and it was already 19 years in service, but it was designed for 75,000 flights. And because of the short distance between the two islands, the plane did much more than this. So it actually, at the time of the damage, it did 680,000 cycles. So almost 15,000 more than was the design lifetime. And this means that it was pressurized and depressurized 15,000 times more. And that's why it failed. And it ended like that.
Oh.
So yeah, it's amazing that they managed to land this airplane. It is amazing that only one person lost her life. It was a steward that was not attached to the seat.
Seat belts.
And this happened actually because of this pressurization. There was a crack that started, it is shown here, started at the corner that propagated because of this loading that was applied. We have also other failures like this drilling platform. It's a huge platform that was in I think the Black Sea, if I'm not wrong here. And this has been destroyed because one of the legs here that have been braced was not well done, and there was a crack that propagated. So this D6 failed, and since this failed, the whole structure went upside down. And after, of course, all these are after post-mortem analysis, so that it was a fatigue failure as well here. This is what happened. So I told you to remember this date before the 1842, because now in 2017 we had exactly the same failure, and this is why I said before that after 200 years we don't know a lot about fatigue failure. This is an axle in a train in Australia in 2017, but again derailed because of fatigue. Hopefully it was designed in a redundant way and it was not really derailed, because also it was transferring a lot of chemical liquid inside. But still, what we say, it's after 200 years, we have the same failures as before, and we still try to understand why this happens. So I'm going back now to the history of fatigue. And probably all started when in 1829, this German mine engineer, Albert, understood that the conveyor chains from mines were failing after some time without reaching their strength. So he reported these observations. And then we have the same person publishing the first article on fatigue in 1837, discussing about loads and durability of materials. You see what I have here, that Albert also invented the rope. It's independent, it has nothing to do with fatigue. But the idea of engineers and mathematicians of that time is that they were doing a lot of different things. They were not only investigating one topic, or they were not experts only in one area. They were like really scientists. We will see it also later on for others. So in 1839, it was Jean-Victor Poncelet in Metz, in the French school, that was the first that introduced or used, if you like, the word fatigue to describe this kind of failure. And actually, he was very tired. And he wrote in a book in 1841, he said that any spring subjected to push-pull force will eventually break under a load which is far smaller than the static breaking load. And this brings in mind what we did with the paperclip. We do a loading, a continuous loading, much less than I broke it already. Okay? So we can break something by applying a continuous load without reaching or approaching even the strength of the material. So later on, we had a lot of railing of trains. And as we said, it still happens today. And it was between 1850 and 1870, a German engineer, again, German engineer, Wöhler. Germans at that time were good, not like the football team of yesterday. But realized that the first experimental program, he did the first experimental program on fatigue of materials. And what he did actually, he created the first SN curve. So this is exactly the publication of Wöhler. And we talk about publications now. This is his paper in 1871, where he described what he was doing. He had a very simple machine, rotating machine, where he was changing this load here to create different bending moments in the structure. And then he reported his results. This is what he did. So a typical example of what he did, but today's example is this one. We rotate the structure, the material, it's this one here. We rotate it, and we have a load down there. And then at a certain moment, the material fails. And when it fails, we measure the number of cycles at failure and we put it here. So we know the stress, we know the number of cycles at failure. And then we ask, how can I evaluate the loading effect on the lifetime of the axle? This is exactly the reason, the way to do it. So we do this at a certain stress level. We put here the values. Why do we have here at the same stress level different values? Can you tell me?
Because of different initial defects or initial defect sizes.
So one problem is so actually the experimental scatter. And we have this experimental scatter because we might have initial defects or manufacturing defects. What else? Material discontinuity.
Speak loud, please.
Maybe there is a change in the diameter of the rod.
Sorry, I didn't listen this one.
He said that maybe there is a change in the dimension of the rod.
It can be that the dimensions are slightly different, exactly. When we manufacture the material,
We have to account for the experimental error because we always have the
experimental error. When we put the material on the machine, we might put it a bit misaligned, or we put it in a different way. In testing of specimens like prismatic specimens, we might also change or affect the behavior by changing the pressure of the machine, so the gripping pressure. So there are a lot of reasons for having this experimental scatter.
May have a notch or this concentration point, so it changes.
Exactly correct. Also like that. And what we can see here, we can see that the experimental scatter in fatigue of composites is very, very large, very big. So we see that we have what we call here from 10 to power 3, 10 to 4, 10 to 5, we call it a decade of life fatigue. So in composites, we can accept a scatter of 1 decade of life in testing of composite materials. If you test a metallic structure, probably this scatter is half of that. But in fatigue of composites, it is accepted to see damage, to see, lifetimes that range between 2 different decades of life. So the same, if we want to continue how to derive these curves, is by doing then a test at a lower stress level, then we define the cycles at the lower stress level and so on, and we define this SN curve. And then this same curious guy, okay, not this one, but this one, started thinking, what about intermediate stress levels? Because initially what we did, if we go here, we tested and we reported the test results, but we don't know what happens in between. And then it was, I said, no, not him, this one, but start thinking what about intermediate stress levels. And then in 1910, so 100 years before today, it was another engineer, Basquin, that introduced the experimental law of endurance tests, as they called it, and it was reported in the proceedings of the ASTM again, in 1910, as I said. And it is actually the logarithmic or log SN curve. So it's an equation saying that if we plot the stress maximum or the stress parameter with a number of cycles in a double logarithmic scale, then it is a line that can simulate the behavior of this material. And guess what? We still use the same equation today. This is the basic SN curve equation that we are using even today for composite materials and even for metallic materials. And although this equation is you see, it's a fitting equation, it can be estimated by linear regression, but it has some physical meaning. This is reported in one paper from Freudenthal in 1946. And you can read this, that the relation expresses the effect of a general mechanism of fatigue and is more than purely empirical, which is the best fit. It's suggested by the circumstance that it is valid for practically any kind of material, whatever its deformation performance. So it has some basic physical background. So what we did, we investigated, up to this point, we said how we define the material performance, but we didn't say anything about the mean stress effect. The testing that we do can be a different mean stress. Do you have this idea in mind? What does it mean, a mean stress, and how does this affect the fatigue life? Can we see this? This is a fatigue loading that I have here.
The average between the maximum and the minimum stress.
So this fatigue loading here is done at
The mean is the average.
Hmm?
The average between the maximum and the minimum stress in the cycle.
So what is the parameters of the fatigue loading? We have the maximum stress as we defined before, which is what we report here. We have the stress amplitude, which is from the mean to the maximum. We have the delta stress, so the stress range from maximum to minimum. We have the mean stress, which is the mean stress, the average stress. We have the frequency of the loading. So if we change the mean stress, this load that we see here, it's a mean stress 0, which means that it is reverse loading from positive to something negative. And in this case, it's from plus 45 to minus 45 Pascal. So in this case, we define, so what I saw here is this stress level. If I change the mean stress, it means that I can go to the same maximum, but to a less damaging minimum. So this stress level for me, it has an average stress at 25, so around here, or 30, a maximum again at 45, a minimum at 10. So this is a different R ratio. Right? The R ratio that you see here is the ratio between the minimum and the maximum. And what you see here is R ratio 0.1, so it might be this case. What would be, can you tell me what would be the R ratio for this blue loading?
How much?
I defined the R ratio as the ratio between the minimum over the maximum stress. Okay? Can you define?
Say.
-1.
Wow, speak loud. Again.
-1, professor. Or 1, if you take the absolute value.
It's minus, how much? -1.
Yeah.
Correct? Because we come from minus 45 to 45. If we divide minus 45 by 45, is -1. Huh? So we have different stress ratios. And what we see in the material behavior for these different stress ratios is exactly different behavior. The material behaves differently. It can sustain much more loads. At here we have 0.5 because this case is probably this one there, the gray, instead of 0.1, which is this case, the orange case, which says here. And this happens because although we have the same maximum stress, we have much more range, much more deviation between the maximum and the minimum for the R 0.1. So one thing that we can do is that we can test the material at any possible combination of R ratios. One other thing that we can do is to search for a good man that can help us solve this problem by having an equation. And actually there was a good man that was called Goodman. He lived between 1862 and 1935. He was a professor in civil and mechanical engineering at the Leeds University. And he suggested that there is a relationship between the sigma alpha and sigma m. Sigma alpha, you remember it was the amplitude of this, and the sigma m. And he said that it's, and also the strength of the material. And he suggested that it was a linear relation between these. So having this means that we can interpolate between known R ratios and estimate the lifetime of a material at a different R ratio, different condition. This has been introduced in 1904, so 100 years ago. Today we know that it does not work well for composites. It is still working well for metals. In between, we have other cases, other people, instead of Goodman, not so good man, like Gerber or Soderberg, that they introduced nonlinear equations for this. And today we know that for composites, we introduced the so-called constant life diagrams that are relevant to the Goodman diagram, but they have different formats to simulate better the behavior of composite materials. So whatever we said up to now is related to continuous loading. You remember we have a waveform that is going up to failure, but in reality, we know that the loading is variable. If you get outside, you see that wind has a variable waveform, and investigations or efforts have been allocated to the investigation of this variable amplitude loading quite early, starting in 1925 with Palmgren, that developed a linear cumulative damage model to estimate the damage because of different blocks or variable amplitude testing. And you see again, he has also introduced a form model parameter for the Sn curve. Gassner, later on in 1939, emphasized more than variable amplitude loading. 1994, then we have Miner. Probably you remember Miner. You've seen Miner rule. This is the Miner rule. Actually, Miner reintroduced the linear cumulative damage rule from Palmgren. And that's why in some books that are quite fair with Palmgren, they say the Miner-Palmgren rule, and not only the Miner rule. And we had also in 1968, some Japanese scientists, first of them were Machuisi and Endo, that introduced the rainflow counting. So the idea is how to measure how many cycles we have in every variable amplitude loading that we meet in reality. And they were inspired by the way that the raindrops fall in a pagoda. And so it comes down. And this is exactly what they do in cycles. When it comes down like that, they count a cycle in between this. So that's why they call this method the rainflow counting method, because it measures the cycles in a way that the raindrops go down the pagoda roofs. And in parallel to these investigations, where we can call them also phenomenological or empirical investigations, we have also the fracture mechanics modeling. It is related to cracks. We investigate the crack and how the crack propagates. And we have the first introduction of fracture mechanics in 1920 by Griffith, reintroduced or going one step further in 1957 by Irving, and then went to more complicated situations like variable amplitude loading. Between 1960s and today, Scrive, this professor in TU Delft, emphasized on the testing of aircrafts based on variable amplitude loading. You will see also a gradual change between the continuous loading to variable amplitude loading, and this is also because of the change in the machines and the controllers. Until 1950, 1960, we couldn't do complicated loadings. We didn't have the computational possibility in controllers, in machines, to control variable amplitude loading. That's why you cannot find these types of loading earlier. And only after the 1960s, 70s, we see the first publications on these variable amplitude investigations. And then here, I have also 1961, where Paris introduced the fatigue crack growth rate in fracture. And he was the first that suggested this quite famous today FCG curve, the fatigue crack growth curve, where he suggested that this middle region here, region 2, has a continuous slope. It's like a line. And this is what we call today the fatigue crack growth curve. So up to now, we didn't say anything about damage. We said, okay, the materials behave like that. We have equations to simulate the behavior. But it was quite early, but in 1900, for example, where Ewing and Humphrey started investigating the damage of materials. They used at the time optical microscopes to investigate failure failure mechanisms in materials. In 1950s, scanning electron microscope brought a great boost in these investigations. And today we have DIC measurements, we have the X-ray tomography. X-ray is exactly the same as we do in medicine. When you break a bone, you go to the doctor, they scan your hand or leg or whatever, and they can investigate and check what happens in your body. And the same happens today with X-ray of materials. You see on the right hand here, the investigation of, so this is X-ray on a adhesively bonded joint with pultruded elements or composites elements in both sides. And in the middle, this dark one is the adhesive. And there is also a crack, so you can see the crack. And these are outputs of X-ray tomography on this joint. So up to this point, we didn't say anything about composites, and our baby here is curious why fatigue is important for composite structures. And there is actually a huge list of reasons where fatigue is important for composite structures. First of all, if you see in composite bridges, for example, someone can say that in a bridge fatigue is not important, and a concrete bridge fatigue is not the most important parameter that we have to investigate. But when we go to a composite bridge, the bridge itself is so much light that the traffic loads or the light loads become very, very important compared to the dead loads. So the load of the load because of the weight of the bridge. And this is one of the reasons for composite fatigue becoming more important than fatigue of other materials. Composites also, you probably know that they are brittle and behave linearly under load, which means that they fail suddenly. So we need to know what happens in the material structure before reaching the failure. And this is why we have to investigate fatigue and be able to model the fatigue behavior, to predict the fatigue failure. Also, fatigue investigations and prediction tools, as we say, help to reduce the cost of structures because we don't need to make physical prototypes. And of course, as you all know, the durability of structures is very important. And this is related to the second point, that they are brittle and behave linearly up to failure. Because if we know how to develop models or predict the durability behavior, then we can also respond to the question when the material will fail. So this is one of the reasons that strengthens the others, and there are more than what are listed here to show that fatigue is much more important for composite structures. One investigation that we did a couple of years ago, we saw that there are a lot of publications on fatigue. You see, in 1955, it was a publication from Hulbert, saying that there is almost nothing about fatigue. And in 2020, we have more than 20,000 publications. Here, it is in 2010, you see, there were almost 10,000 publications. In 2020, we have more than 20,000 publications, which means that we publish more than 1,000 papers per year on fatigue. And in fatigue of composites, we investigate in these publications. Mainly, you see investigations about these points that I point out in the left side on the R ratio and frequency effects, the viscoelastic behavior during fatigue, influence of the constituents, fiber architecture, different materials. Now, a lot of people work on hybrid composites where we mix glass and carbon. Can you tell me one application where hybrid composites is used a lot? We use this hybridization.
Speak loud.
Aerospace industry.
An example?
Again. Again. Say.
Maybe in Airbus H380, they use the hybrid solution like a fiber metal laminates, metal with glass fibers.
Yeah.
Or also like the sandwich structures, they're also a hybrid thing.
In aerospace, you very well.
Wing works on that.
In aerospace, we use the fiber matrix, fiber the fiber metal laminates, FMLs, huh?
Yeah.
Where we have, and the most characteristic example of this is the glare, the glass aluminum,
Exactly.
that is used in a lot of applications, and it has been because the combination of this. Of these layers, instead of using only layers of aluminum, for example, or only layers of glass fibers, gives a much better impact resistance to the material. We've seen a lot of hybridization also in wind turbine rotor blades, or the huge rotor blades that they make today. By the way, do you know what is the size of a contemporary rotor blade?
The size of?
The size of wind turbine rotor blades of today, the big ones. Where are we?
The big one.
Like 90 meters. 10 meters?
Can it?
190 meters. Some no.
180 meter.
Okay, so today we have blades that are more than 100 meters, 105, 110 meters. From
They should know.
LM, so blades of more than 100 meters. And if you see before 20 years, this is another introduction, we can give it in another lecture, but wind turbines, so wind energy, wouldn't be at this stage, or wouldn't be at all energy source that is really attractive as it is today without composites. Because for these huge structures that we have, we couldn't have them without composites, because everything else is much more heavy and much less performant. So if you see the wind turbines before 1980 were made by wooden plates, or by plates with tissue, like the old windmills, and they were not able to produce energy more than the energy that was needed for a house just by the wind turbine. And since the 1980s, where they introduced composites to these structures, we have this huge and progress. If you see the wind turbine industry, wind rotor blade and wind turbine industry, wind industry in general, is probably the most rapidly increasing industry, with more than 15 to 20% increase per year the last years. And this is due to the use of composite materials. And for these huge wind turbines now, the blades of 100 meters, there is a lot of use of hybrid carbon and glass composite materials. So they cannot use carbon because it's too much expensive, and they cannot use only glass because it's not performing well. So they hybridize these materials, and they use carbon where the stiffness should be higher than before, and they use glass in all the other areas where the structural performance is enough. So the hybrid materials in wind turbines is much more used than a lot of other cases. So I'm coming back to these simple questions here. What is the ratio effect? And we discussed a bit before about this. So here there is another video, but there is no need to show it now. It's only fatigue failure. So the ratio effect, we've seen before, there is an effect of the mean stress. This is what we call the ratio effect. And as we said before, we cannot use anymore the linear minor diagrams because they do not work for composites. How we say that they do not work with composites? We have experimental results that show that these equations that are due to the linear diagrams, they are not anymore valid for composites. And we have other types of formulations where we call them the constant life diagrams, like this one. We also have a viscoelastic behavior of composites. And we see these are the hysteresis loops of the material. And we see a drop of the stiffness. So the drop of the slope of this loop shows that the stiffness of the material reduces. And also we see an increase of the area. And the area inside the loop is assigned to the dissipated energy. So the more the area is, the more the energy we dissipate, which means that we have damage in the material, because the area shows for the energy that is dissipated there is due mainly to the friction between the material molecules. And when we have damage, it means that we have cracks, and this friction increases. And that's why this area is increasing. In composites also, what I mentioned it before, but briefly, we don't have a fatigue threshold. You remember in metals, you have a line like that and then a line like that. After a certain stress, the material behavior does not degrade anymore. In composites, is documented in the literature that we don't have this fatigue threshold. We talked also about the influence of the constituents here in the fiber architecture. So on the left hand here, I have a graph showing the effect of the fiber architecture. We have materials at 0 degrees, the same material at 15 degrees, and the same material up to 90 degrees. And we see how this affects the behavior of the material. On the right side, I have the same fiber architecture, but different materials, starting with carbon, the blue one, and then glass is the yellow one. And then what else is here? So we have this is biofiber. What is important here to show is that, first of all, the materials that are better in performance, like carbon, show also a very, very low slope in the S&N curve. The materials that are not so good show bigger slopes on the S&N curve, which means that the effect of, if we test at high stress levels or low stress levels, we can increase the life by far in the good materials, not so much in the less performant materials. And if we compare, here is a comparison between aluminum, which is the blue, and then GFRP and CFRP. You see again the difference, the huge difference between the properties. This comes to confirm what we said before, that composites perform much better than the other materials at a lower density. And this is why when we talk about composites, probably you have already discussed about this, we talk about the specific properties of the materials and not the absolute properties of the material, where specific property is the property of the density of the material. And then we have fracture mechanics. We have the material with a crack somewhere, and the crack propagates because of loading. And we can have loading which is, we can have loading which is due to opening of the crack, where we see here, which is called the mode 1 loading. We can have loading where we have sliding of the crack, which is called the mode 2 loading. And in a lot of cases, we have mixed mode loading conditions, where we have a mix of opening and sliding. What we can extract from these materials is exactly the FCG curves. So remember the Paris law that we discussed before. We have the FCG curve for the material. And you see here that even in these materials and in this behavior, there is an R ratio effect. And there are models, again, like the models that we had before for the CLDs, to predict this behavior. I will not bother you a lot about this. I will just go to this video here, which shows that this is a mixed mode fatigue of a sandwich panel. So actually the beam of a sandwich panel. What you see inside here is a balsa wood. Outside you have glass substrate. And this is how it works. And what we see here also is some fiber bridging, fibers coming out. So if you are interested in fatigue, you have to be patient and wait until this structure here reaches 2-3 million cycles. And at the same time, you have to be patient to go there and measure the crack. So this was at 5 Hertz. And now we change the loading frequency to 10 Hertz. Okay. Did you like this test?
Tassos, we faced some problems seeing properly the video, because I think Zoom, if you don't change to optimize video mode, I don't know where it is, this option. We can see the video with a lot of pauses.
Okay, doesn't matter,
but we catch it.
Okay, the idea is that you have this video.
Yeah, you get the idea.
Yes. So to get this video and to get results that give you curves like this, you need to run the test for 5 or 4 or 5 million cycles. About 5 Hertz, 5 million cycles means around 10 days. So be patient enough to be there 10 days, measuring the crack, investigating if the material is progressing well, the test is progressing well. Cross your fingers that you don't have a failure in electricity or whatever else. And this is how we do fatigue investigations. I will conclude here this discussion, this lecture, by saying that I hope now that you understand that fatigue failures are the most common in components. We know that fatigue is a big problem in design of engineering. We don't know a lot about fatigue, and this is good because we can still work on this until our retirement at least. Fatigue failure is a combination of different events. We have effects of course, load, environment, the geometry of the material architecture, material, as you very nicely said, manufacturing defects, a lot of complicated events that happen there, and that's why fatigue is still a problem, and we cannot investigate it, or we cannot give commonly, if we call commonly accepted tools for fatigue design yet. Still, although we don't know a lot, there are a lot of different approaches in fatigue, and actually now there are some methods to some guidelines, if you like, to design fatigue of composites, but it's not yet there. So yeah, for those interested, a PhD in fatigue might be a very good choice. And with this, I think I finished. I hope you enjoyed. And I will be at your disposal if you have any questions.